Welcome back, everyone. I'm going to talk a little bit about something we discussed yesterday, looking at the combustion wheel and how this can help us to understand the relationship between events that are happening in the engine, right? We want to understand where the piston is in relation to the crankshaft, or at least that particular crank pin. And we really discuss things in terms of degrees of crankshaft rotation to establish for ourselves a timeline for where these events are in the course of time. And that way we can better understand when we're dealing with valve adjustments and engine timing, things like that. So something that pops up quite a bit is taking a look at our combustion wheel and trying to determine the distance of crankshaft rotation in between specific events. So what I have drawn out for you here is our combustion wheel of a slightly better quality, since I took some time to draw this. But we have everything that should be somewhat familiar laid out here. We have top dead center, which is up at the top. We have 90 degrees of rotation. Bottom dead center, which is the lowest point of piston travel. We have 270 degrees of rotation, and then back to top dead center. Now you'll remember, with a 4-stroke engine, a complete combustion cycle is 2 full rotations of the crankshaft. So that means we're looking at a total of 720 degrees of rotation for a single cylinder to complete its combustion cycle. We'll talk more how that connects with things later on, but right now we're focusing on a single cylinder. 720 degrees of crankshaft rotation will complete one full 4-stroke cycle. So I've listed a few different events on this combustion wheel so we can determine the distance between. And it just takes a little bit of light math to be able to accomplish this. So starting off with our intake stroke in blue, we have the exhaust valve closing at 20 degrees after top center. We have the the compression stroke next, where our intake valve is closing 15 degrees after bottom center. We have ignition happening up at the top of the compression stroke, 25 degrees before top dead center. Then we move on to our power stroke, where the exhaust valve is going to open 30 degrees before bottom center. And then our exhaust stroke, where up towards the top, the intake valve is opening 50 degrees before top center. Those are our major events. Now what we're going to find out is the distance in terms of crankshaft degrees of rotation between these events occurring. So what we have is our valve overlap, our intake open to intake closed event, exhaust open to exhaust closed. We have intake closed to ignition, ignition to exhaust open, and then exhaust closed to intake open. So let me show you how this works, and then I'll show you a little bit of a cheat we can use later on. So for valve overlap, this is one of our easiest ones. We're really just looking at the distance between two moments in this combustion wheel. So we know that our exhaust stroke right here is going to go directly back to our intake stroke. Draw a line here so you can remember, right? We go straight down to our intake stroke. That's what happens next. So the two closest events here, remember that valve overlap is the time when both our intake valve and our exhaust valves are off of the seat. That's going to occur between when the intake valve begins to open over here at 50 degrees before top dead center, and when the exhaust valve closes at 20 degrees after top center. That's when both valves are off of the seat. So all we're going to do to figure out what our valve overlap is take this 50 degrees before top dead center and add it to the 20 degrees after top dead center, right? We're trying to measure the distance. We'll draw this in here. We're trying to measure the distance between these 2 points, just like that. So we can just simply add those 2 degree measurements together. So in this case, we have 50 right here plus 20 degrees. That is going to give us 70 total degrees of crankshaft rotation for our valve overlap period. Simple as that. That's really the method we're using to calculate everything. Just sometimes we get a little bit confused about how the strokes are going to factor into this. So let's take a look at another relatively easy one. We have our intake open event to our intake closed event. So here we have intake open, which happens 50 degrees before top center. We go through our intake stroke, and then 15 degrees into the compression stroke, we have our intake close event. So in order to add this up, the easy way I like to do it, call it a life hack or a cheat or whatever you want, I'll take the intake stroke. I know that the intake stroke is 180 degrees, so I'm going to add 50 degrees, right, because that's how far we are before top center on the exhaust stroke, and then 15 degrees, since that's how far we are into the compression stroke. So 180 plus 50 is going to be 230, plus another 15 is going to be 245. So we have 245 degrees of crankshaft rotation between when the exhaust valve opens and when the exhaust valve closes. Or in this case, we have 245 degrees of crankshaft rotation in which the intake valve is off its seat or open. Next, let's take a look at the exhaust open to exhaust close event, like I was mistakenly saying before. Again, with exhaust close, we know this is going to happen 20 degrees after top dead center on the intake stroke. So that's 20 degrees into the intake stroke. Similarly, on the other side of our exhaust stroke, our power stroke, which comes right before it, our exhaust valve begins to open 30 degrees before bottom center. So 30 degrees away from bottom center is where our exhaust valve starts to open. So again, the math for this is relatively simple. We know that our entire exhaust stroke is 180 degrees. And since we have a closing and opening event that is 20 degrees into and 30 degrees into the intake and power strokes, we can add those numbers to 180 to figure out what our math is on this one as well. So again, similarly, we're going to take 180 degrees for the entirety of the exhaust stroke. We're going to add 20 degrees because that's how far it goes into our intake stroke before it closes. So we have 180 plus 20 is 200. And then we have 30 degrees before bottom center on our power stroke when the exhaust valve opens. So we take that 200 degrees, we add 30 to it, and we come up with 230 degrees total. Again, that is 230 degrees of crankshaft rotation in which the exhaust valve is open. Next, let's take a look at the difference between our intake closed, when the intake valve shuts, and when we have our ignition, right? This one can get a little bit trickier because we're looking on the same strokes. We have to do a little bit of extra math, but it's not bad. Again, we know that this entire compression stroke is 180 degrees. Similarly, both events, both our ignition and intake closed events, are going to happen on that same stroke. So all we have to do is subtract. We can take 180 degrees and subtract 25 degrees because that's how far our ignition takes place before top center. So 180 minus 25 is going to be 155. Next, to figure out the distance between the two, we need to subtract the amount of degrees of travel from the intake closed off of that compression stroke. So we have 15 degrees after bottom center on the compression stroke. So we take that 155 we've determined, we subtract another 15 degrees off of that, and that gives us 140 degrees. So again, to answer that, we have 140 degrees of crankshaft travel between those two events, or in this case, we have 140 degrees after the intake valve closes prior to ignition happening. Now, there's two more we're going to take a look at. We have ignition to exhaust open, and then we have exhaust closed to intake open. So this is where it can get a little bit tricky because now we're moving across multiple strokes as we look at this. So again, similarly, we have ignition occurring 25 degrees before top center on the compression stroke. Our exhaust valve is going to open 30 degrees before bottom center on the power stroke. So again, the easy way to do this in my mind is I take my power stroke, that's where most of this is going to occur. I take my power stroke over here. I know that's 180 degrees, so I'm going to subtract that 30 degrees before bottom center on the power stroke for my exhaust valve opening. That leaves me with 150 degrees. Now I need to adjust this slightly because our ignition event is actually taking place on the stroke before it. But since I've already figured out how much travel we have on the power stroke, which is 150 degrees, I just need to add the amount of travel on the compression stroke, which is 25. So I can take 150 plus 25, that gives me 175 degrees. Easy as that. All right, now let's try a really tricky one. We're going to take a look at the difference between the exhaust valve closing and the intake valve opening. This is where it gets a little weird because we cross quite a few strokes of the combustion cycle on this one. So again, watch carefully as we figure this out. We know that our exhaust valve is going to close 20 degrees after top center on the intake stroke. That's the first stroke that the engine goes through. We know that our intake valve is going to open 50 degrees before top center on the exhaust stroke, which is our very last stroke of engine rotation. So let me show you the easy way to figure this out. I like to take the entire thing as a whole. I know that for the whole combustion cycle, we have 720 degrees of crankshaft travel, right? So I can take this 20 degrees into the intake stroke, where the exhaust valve closes, and subtract that from 720. Simple as that. It gives me 700 degrees. Next, this intake valve opens 50 degrees before the exhaust valve is finished. So I'm also going to subtract that from my overall combustion, or the degrees of travel for the overall combustion cycle here. So we have 700 degrees after subtracting 20 for our exhaust valve closing. We're going to subtract another 50 for the intake valve opening. That's going to give us 650 degrees of crankshaft travel between the exhaust valve closing and the the intake valve opening. You'll also notice that the thing that makes math really simple on this is the distance between those two events. It's just the entire combustion cycle, 720 degrees, minus our valve overlap, which is 70. Pretty easy. That's kind of my way of cheating around this to try to figure out the math without having to get too reliant on the calculator. I think it simplifies things a little bit. And you can use this to help you navigate the entire combustion cycle and all of the events happening within when we try to talk about engine timing and valve timing. So thanks for watching, and look forward to doing the next video.